Good. That's very wonderful, guys. Nice to see you all, or those that I can see. And let's begin. We are doing conditional probability. You may, of course, use for exam 1 conditional probability, but would be nice if you can think in many, many terms. You see, just as many solutions as possible for a problem when you do it for yourself might get you a better intuition. So I think we are here. So the idea, guys, with probability is that all probabilities are conditional probabilities. Why? Because any experiment, when you toss a coin, you are assuming you know everything about this full universe except the outcome of the coin. Good? That's essentially what you do. So you don't throw information as irrelevant. You assume that you know more than you in fact do. And the idea is that you have, it is my idea, that you have a very, very elaborate document where everything is filled in except for the outcome of that coin, if you're studying the throwing of a coin. Oh, I see it's a show and tell of cats. I see now, right? That's good. So this is the way I think of any Kafka protocol, is that it's really infinite. But when you're studying situations where you have only finitely many outcomes, that means that only a few boxes remain unfilled. Understood? And we gave an example of that. Let's just see that example again, guys. 52 cards are dealt equally to 4 players, east, west, north, and south. We know that north and south have a total of 8 spades among them. What is the probability that east has 3 of the remaining 5 spades? So when I solve this question, I assume that I know the specific cards that are available to, I think, east and south or whatever, right? East and south, whoever else is there, right? So that I assume that I know the specific 5 spades that are available, and I assume I know the specific other cards available. The idea is that you can imagine yourself jumping from universe to universe, and in different universes those would be different 5 spades along with a different collection of 21 known spades. And in each universe, when you calculate the probability, it's the same probability. You understand? Right? So I'm hoping you understand, guys. At least that's how I imagine it, right? So that allows me to fill in the documents except for a few boxes. And we calculated that probability to be 5 choose 3, 21 choose 10 divided by 26 choose 13. Right? So in other words, we know that 26 cards shared among the 2 players, and then the numerator is the success combinatorics for east having exactly 3 cards, 3 spades. Good. Now we talk about a very important theme that's called the multiplication rule. So why do you multiply probabilities? Some of you multiply probabilities all your life, but do you remember why? So here is the situation. So if I have events within S, and if I want to calculate the probability of the intersection, I might as well calculate the probability of event 1 multiplied by probability of event 2 given 1, that the 1 happened, then multiply by probability that E3 will happen given that E1 and E2 happen, so on. Why does this work? You can establish that by looking at the algebra. Do you see what happens, guys? I can write a telescoping product. Look at it. P of E1 multiplied by P of E1 E2 over P of E1. You can see that here they would cross. And then multiplied by P of E1 E2 E3 divided by P of E1 E2. So you can see that blue cross, the black cross, the purple would cross, and somewhere eventually the green will cross. And the only thing surviving is that last sentence. I hope you can establish that. It's pretty easy. Begin with 2 events, 3 events, and you notice the pattern very rapidly. You see what I did? telescoping sum. We're assuming, of course, that each of those probabilities are non-zero, because otherwise the total probability is zero and this calculation is meaningless. Good. So what is this? This is just P of E1. What is this? This is, look at it, the same thing as E2 happening given that E1 happened. That's the definition of probability, of conditional probability. This is the definition that E3 happened, that E3 happened given that E1 and E2 happened, and onwards. You see, that's how we get that multiplication formula. That's why in probability, that's when you multiply in probability. Good? Now, let's consider this example. Urn contains n balls numbered 1 through n. K balls are removed sequentially without replacement in such a way that at each step, any one of the remaining balls is equally likely to be chosen. Show that each sequence of k distinct numbers is equally likely. You understand? I just try to reformulate all sorts of different notions of randomness. In this case, we have at each step of sampling, you have a randomness relative to what remains, right? Now, initially, we assume that when you pick an ordered sequence, picking it is random if each ordered sequence is equally likely. So we consider the sequence as a whole. Here we consider one element at a time. Good? So for that purpose, we can verify that very simply. So there are, of course, n choose k times k factorial sequences possible if you choose k elements. Do you agree? N choose k being the balls removed, k factorial will represent the various orders by which those balls were removed. Good? So if the sequences are truly this way generated at random, then each sequence has probability of 1 divided by n choose k times k factorial on the denominator. You'll agree. So here it is, right? So that's what we're going to establish. So let's consider the probability of drawing the sequence 1, 2, 3, all the way to k. Just this sequence. What would be the probability of drawing that sequence? Well, it will be simply the intersection that I withdrew E1, 1 at the first choice, E2 as the second choice, E3 as the fourth choice, the third choice, and onwards, right? And by conditioning, what do we get? We get first ball to be picked is 1 over n. The second ball is still there. Given that 1 was picked, there are n minus 1 choices. So it's 1 over n minus 1. And you continue. And what do you see in the denominator? The product of the denominator is the same as n choose k, k factorial. Good? And we use the randomness at each instance of sampling. And of course, if you pick, it's pretty trivial. Pick any other sequence in any order. Clearly, those numbers will be the same. You agree? So, I mean, it's almost a trivial verification. I just want to show you that all those notions of randomness agree, as our intuition tells us that they should. So now let's return to the matching problem. We don't have to do it from scratch, guys. Do you remember the matching problem? That is where you have gentlemen wearing hats. They then select the hats from a pile randomly. And the problem is calculate the probability that no gentleman will pick his own hat. You remember what we obtained. If the number of gentlemen goes to infinity, if it's very large, that probability is 1 over e, or e to the minus 1. You remember that, guys? How we set it up? We just very simply said, well, suppose we want the probability that gentleman 1 doesn't wear his own hat, and 2 doesn't wear his own hat. So we symbolically constructed intersection of events, and we calculated this way. So in this exercise, we want to know the probability that exactly k gentlemen select their own hats, or k is smaller than n. So we have, let's say, 1 gentleman or 2 or 3, but and others do not. Good? Do you need a review of how we derived the previous result? The gentleman having n hats? You do? I was hoping you said, no, of course we don't, right? We understood it so well, no need to review that. Okay, let's do it. What can I do? Then let's do the calculation. Here, guys, so suppose we have gentleman 1, 2, all the way to n. We want the probability no one wears own hat. Good. So let's suppose that we have E1, E2, En, where E sub j means gentleman J, J wears his hat. You understand the problem, guys, right? So they randomly pick a hat. So EJ is gentleman J wears his own hat. What probability are we interested in? If nobody wears his own hat, then that's the probability that person 1 doesn't, and person 2 doesn't, and person all the way to person n not wearing their own hat. Yes? Now, we remember the De Morgan laws, correct, guys? The De Morgan laws, if it's the intersection of complements, that means that, it means what? It means the same thing as the probability of E1 union E2 all the way to union En complement, which is of course the same as 1 minus the probability E1 union E2 union En. Are we all understanding this part? De Morgan laws, guys, right? It's a matter of logic, right? So if none of them wear their hats, that means that it's the complement of somebody wearing their own hats, right? Nobody wears his hat means it's not true that person 1 wears his own hat, or person 2 wears his own hat, or person 3 wears it, because the or sentence, it's true as long as one instance is verified, right? So that's why this is so obvious, I hope. So we have 1 minus this. Now this probability involves union of non-disjoint events. Do you agree? If person 1 wears his own hat, it doesn't preclude person 2 wearing his own hat. So that's not disjoint. So we need to use, for that purpose, we need to use inclusion exclusion formula, right? How do we deal with probabilities that involve unions? So this part, so I'll put a line here. So now probability of E1 union E2 is what? This is by the inclusion exclusion formula, guys, which I hope you understand. How do you understand it? You begin by working with 2 events, then work with 3 events, and you can see the pattern is very obvious, okay? You can very quickly, by induction, generalize it if you have to, right? It's just very easy to notice this pattern. And the pattern is that it will be a summation where R starts at 0 and goes all the way to n of -1 to the power of R. Or maybe we'll do it like this. So R goes from, maybe I'll better to put it, R going from 1 to n, and that would be R plus 1. And then here we have summation I1 less than I2 less than IR, probability EI1 EI2, EIR. Now, this might look scary. It's not scary at all. What is this saying, guys? This is saying simply, you see, when R is 1, then -1 is to the power of 2, so there's no -1. And that R is 1 means add up PE1 plus PE2 plus PEN. Subtract all possible combinations of PEI1, EI2, and then add and onwards. You understand? Subtract, add, etc. So what you do is you add each probability of each event separately. Subtract every pairwise intersection. Then you would add every triple combination of events. You understand what I mean, pairwise intersection? So you subtract person 1 and person 2 wearing hats, and person 1 and person 3 wearing hats, and person 2 and 5, and any combination of any 2 people. And then you add any combination of 3 people wearing their hats, and subtract any combination of 4 people wearing their hats. And then you continue doing that until you reach the number of gentlemen n. You understand? The last term you consider is the intersection of all of them. Clear? Now, there is a lot of symmetry here because there is no preference between one gentleman. There is no preference. Probability of gentleman 1 wearing his own hat is the same as probability of gentleman 2 wearing his own hat, and any intersections between gentlemen I1 and I2 is the same as the intersection of 1 and 2. Do you see that? Right? If gentleman 2 wears his own hat and gentleman 7 wears his own hat, it's the same probability where person 1 and person 2 wear their own hats. Do you see that? That's the symmetry. So to make this expression even further simplified, I use that symmetry. Are you with me? Right? So what do we get, guys? So by the symmetry, I can just say this is the summation where R goes from 1 to n, -1 to the R plus 1, and I can replace the summation, right? So the summation, this summation, I1, I2, all the way to IR, because I am essentially adding the same number, right? Adding the same number. So how many times do I add the same number? By symmetry, probabilities that I'm adding are the same. How many times do I add the same number? I1, I2, I3, and whatnot. How many times? How many pairwise? How many triple combinations? How many combinations where R people are wearing their own hats? You see, because at any R is 1, 2, 3. How many combinations where R people are wearing their own hats? N choose R. Thank you, Aaron. Everybody says it, guys. Guys, N choose R. Anyone doesn't see it?
Yes, I have a question.
Go ahead.
Besides your weird faces, the E1 and E2, like when you talk about the instance where they happen together, like the second part, minus part,
Yes.
like what does that entail? Like you can't have one person and the second person having some commonality with each other.
Well, inclusion, exclusion, this formula, so this formula tells you you have to subtract intersection of 2 events, yes? So E1 and E2 means person 1 and person 2 are wearing their own hats. So you added probabilities of individual person 1 and individual person 2 and individual person 3 where they are wearing their own hats, right? This could have included, if person 1 was wearing his own hat, that could have included also probability of, or they could have included person 2 wearing their own hats. The events E1, E2, E3 have intersections. So I have overcounting there. I need to remove things that I overcounted. Right, so this inclusion exclusion formula tells you how to do that, because you can do it systematically. You understand? If you verify it for 2 events, you can then extend that verification to 3 events. You can see the pattern. You can prove it by induction that this is correct. You can also come up with a combinatorial problem, I think, but combinatorial argument, but you can prove it by induction. So the inclusion exclusion formula, very useful. Good.
Can I ask a clarifying question about the formula as well?
Yes.
So this is, we're multiplying the summation of -1 times the summation of the probabilities. Is that correct?
So we're not multiplying anything as of yet at all, right? We're not gonna, for this example, we will not use multiplication of probabilities of events. I'm not using probability of intersection here, right? I am having the inclusion exclusion formula, and I'm trying to simplify it.
Right. I'm looking at like where like the summation of -1 to the r plus 1, and then there's the summation of the probabilities.
Right. That means this. So this is the main summation, right? So when you set r equal 1, this will be the -1 to the power of r minus 1. It's just going to be a positive number, right? The point is that this changes from positive to negative. That will mean if r is 1, add up all the separate events. Add up E1, E2, E3. You would have been done here if the events were disjoint, but they're not disjoint. So then you have to subtract. And what this would mean when r is 1, when you subtract, now r is 2. That means you have I1 and I2. You have combinations of 2 numbers, the 2 people, right? Which you can always arrange with a person with smaller index being considered to the first, the set listed first, and the person with bigger index is listed second. That's why I'm saying I1, I2. I1 is less than I2, I2 is less than, etc. Right? So it's going to always be plus, minus, until you reach to n.
Okay.
And then the pattern stops.
But does the r value in any way influence the second summation?
Well, sure, because sometimes it makes it, you subtract the summation and sometimes you add the summation. If r is 2, for example, then you subtract, because -1 to the power of 3 is -1. So essentially what r is, what this part of the summation is doing, the minus part here, is deciding whether you add or subtract.
Okay, I understand.
You simulate it to as -1 to different powers, because if you take -1 to an even power, it's 1. That means you just add. If you have -1 to an odd power, you subtract.
Okay.
That's all it does. I hope that helps.
It definitely does. I understand it conceptually, but I'm having trouble, like, why you do it.
Why? Because, why am I doing it? Because I want to calculate this union, and this union is not simple, right?
No.
I cannot say probability of first plus second, so this formula works. And how do you verify the formula works, guys? So you should sit and do the expansion for E1 and E2. What's the expansion? Then if you know the expansion for E1 and E2, you should be able to do the expansion for E1, union E2, union E3. It's very easy extension of that idea, okay? Just applying, basically when you have union of 2 events, so if you have union of 3 events, that can be collapsed to union of 2 events, and where you apply again that formula you extracted for 2 events. You can break it by unions of 2 events at the time, and you will obtain this formula. Good? So we have r1 to n minus 1 to the r plus 1. And because we're adding the same number, that would be n choose r. For any r, we have n choose r, and the summation can be then collapsed to e1, e2, er. Because it doesn't matter which specific sets, as long as we have r of them at the time, right? So this is already much simpler. Now this I can easily calculate. This is what? This is summation r equal 1 to n minus 1 to the power of r plus 1. And then this is n choose r. And what is this probability? Now, I'm not using multiplication. I could have, but we haven't developed it as much yet, right? So what I'm using is this idea that all sequences, we saw that there should be the same. All sequences are equally likely. Now, we consider here sequences that are identity up to R and can only be different from R plus 1, R plus 2, except only those people among themselves might not choose their own habits. They're n factorial sequences. What do you put on the numerator, please? If you understood what I'm saying, what do you write on the numerator? You see, guys, E1 intersect E2, intersect E3, intersect ER means what? It means that we are dealing with all sequences where person 1 is assigned to hat 1, person 2 is assigned to hat 2, person 3 is assigned to hat 3. Do you see that I didn't do the Kafka protocol, but I imagine the document is person 1, 2, 3, 4, and then the hat numbers below are switched. Possibly, right? But here we have under person 1, I write 1 in my document. Under 2, I write 2. Under R, I write R. And the only freedom I have is remaining boxes. How many remaining boxes do I have? I have n minus R remaining boxes. You all see that. N minus 1 minus R remaining boxes. And the corresponding symbols for them. So how many permutations on those symbols are possible? N minus R factorial. Thank you, all of you. I hope you see it, guys. I mean, I only see 3 people that responded. Do the remaining ones, I mean, you consider it too easy to respond, correct? That's why you don't write it. Or you don't understand. Let me know, guys. I mean, I'm not sure if you're embarrassed by such things, but there is no reason to. It's a difficult subject.
Do you mind explaining it again? The n minus R.
Yes. So first, this is n minus R factorial. You have to, guys, when you solve those problems, that's pretty much the only reason I am able to solve anything. I am much slower than you at any of those things. If you ask me to go to the cashier and pay for anything, the money looks the same to me. Maybe because I'm Russian, you know, what we do is we just throw them like this. Once we have something, we just toss whatever we have from the pocket and that's it. So I am not good at counting. The only advantage I have is, well, I can think a little bit like a bureaucrat. I can just clearly think, what am I talking about? Good. So here is my Kafka protocol for the situation, right? I am documenting who is wearing their hat and who is not wearing their own hat. Agreed? So my document is looking like this. So here I have gentleman 1, gentleman 2, all the way to gentleman n. You agree? And the hats are labeled also 1, 2, 3, 4, 5, etc. Good? So when I put in all the possibilities of how hats could be distributed, you see that there are n factorial possibilities in my sample space, because the first person can claim any of n hats. Second person can claim any of n minus 1 remaining hats, and so on. So there are n factorial possibilities. Now, when I consider success protocol, basically when you consider E1 all the way to ER, success protocol. Remember, in the numerator, I count documents that correspond to success. How do those documents look like? So those are, I can use the same document form. So it would be 1, this would be 2. Then somewhere over here is R. Then R plus 1. and all the way n. Except, do you see what I'm saying, guys? Except that this number is printed to be 1. This number is printed to be 2, and all the way to this number printed to be r. So most of the boxes, not most, sorry, but some of the boxes are already occupied. I have no access to them. That's a success protocol. You agree? Anything I put in the remaining boxes, if I do it correctly, I'm not allowed to use 1, I'm not allowed to use 2, I'm not allowed to use 3, all the way to r, because I'm allowed to use each number in the box exactly once, right? So only one box contains contains the number 1. Only one box contains the number 2 in my general protocol. Do you all see that? Because I'm not going to have people fighting for hats. Yes, they're not fighting for hats, they're gentlemen. Exactly. Good. So how many available spaces we have? We have how many symbols available, guys? We have n minus r symbols available. Do you all agree? N minus r symbols available, and n minus r spaces available. So that would be n minus 1, sorry, n minus r factorial. Not minus 1, n minus r factorial. Clear? Well, I hope very clear, guys. I hope. It's much easier, right? If you've pictured it, that's all I taught you guys, right? The Kafka protocol, because other than that, what am I able to tell you? Just if you understand what you're counting, then you should be able to document when something is correct and when something is not correct. Just you have a paper that that is a testimonial to what happened. So we have n minus r factorial over n factorial, which I can simplify and write as r equal 1 to n minus 1 to the r plus 1. What is this, guys? This is the same as n factorial divided by r factorial. And here we have n minus r factorial. That's the n choose k, n choose r, sorry. And here I have n minus r factorial over n factorial. What survives out of this mess? Only 1 over r factorial. So look how much I simplified and how nice it looks. Now I see that my probability is the summation r equal 1 to n minus 1 to the r plus 1 divided by r factorial. Now what is this? This is simply probability E1 union E2 union all the way. So what is this? If I subtract 1, guys, if I subtract 1, that is 1 plus r equal 1 to n minus 1 to the power of r divided by r factorial. Are you with me? You see, it used to be r plus 1, but now if there is an extra minus 1 here, it will be r plus 2. But r plus minus 1 to the r plus 2 is the same as minus 1 to the power of r, because powers of 2 eliminate minus 1. Are you understanding? Are you with me, guys? Do you see why it's 1 plus minus summation of minus 1 to the r over r factorial? I'm hoping I'm saying something very simple. Confirm that you understand, please. It is negative 1 to the power, or did I write something else? It's minus 1 to the power of r. So you see, you subtract 1. If you subtract 1, you multiply the summation, all the summation by minus 1. If you multiply the summation by minus 1, you can push it into each term. You can push it into each, you just multiply this by minus 1. So what happens here, now you would have minus 1 to the power of r plus 2. Now to the power of r plus 2 is the same as to the power of r, guys. You remember that minus 1 squared is 1. Yes? We don't need a calculator for that just yet. I mean, in a year, yes, of course, right? But not today. Good? So what is this, guys? 1 plus the summation is the same as 1 to the power of 0 divided by 0 factorial. So I can write the sum as simply r0 to n of minus 1 to the r over r factorial. And I look at the summation. If I make n go to infinity, I recognize that this approaches e to the minus 1. If n is large, this looks like e to the minus 1 because you all remember how to extract the Taylor series of e to the x, correct, guys? We went over that several times, and you have it on my notes. So it's e to the minus 1. Now we can return back to the current material. Good? The review, you see, guys, you can do it on your own. You don't need my notes for that now, yes? Now, here we are interested in the situation where we want to allow k individuals to pick their own hats. Exactly k. So we had 0 individuals pick their own hats. Now we want to know what happens if exactly k individuals pick their own hats. Do you agree that, that there is symmetry here? I might as well assume that the last k individuals pick their own hats. The very last k individuals pick their own hats. I could assume the very first, the very last. I decide to assume the very last individuals picked their own hats. No problem there, yes? By symmetry. So by symmetry, it means what, guys? It means that the probability I am seeking is n choose k, the probability that the first n minus k people did not pick their own hats, and the last k did pick their own hats. And why n choose k? Because if exactly k individuals pick their own hats, it could be any k, any particular k. So it's the probability that first k or any other combination. Do you understand why it's n choose k times that probability? I'm hoping I don't need to explain it. Yes, guys? Cool. It's just we're adding a lot of similar probabilities. In this case, what we're adding are disjoint events, because if people 1 through 3 pick their own hats and the rest did not, or 2 through 4 and the rest did not, those are disjoint events. All right, so I can just add them up. And since by symmetry, what I add up is the same, I just end up multiplying the probability by n choose k. Here it is. Now here, guys, here I can use conditional probability. Look what we have here. We have here, so what I can simplify it as, look at those events. I can say it's the probability of that. I think of it as 2 events. Maybe that would help you see it, right? So I think of this as my A, and of that as my B. Of this red thing as my B, and of this blue thing as my A. So what I have is simply, what I see here is probability of, well, I can write it as probability of A, B. Good. And by the multiplication rule that we just verified, I hope you still remember it, it is the probability of A times the probability of B given A. Yes? And do you see what it is here, guys? So this is the n choose k, this is A, probability of A, and this is probability of B given A, just written in uglier symbols. Yes? So what is this? So let's look at it, guys, carefully. What is this probability? What is the probability of A? The probability of A is very simple to calculate, this one. Why? Because we are now asking for the probability that that all those people pick their own hats. We have n minus k available possibilities. Here it's the same document, but the last k slots are occupied by the corresponding numbers. You agree? So you all see why it's n minus k factorial over n factorial. This probability is easy to calculate. Yes, guys, you all see that. Some of your, first of all, some of you disappear. I do not know why, guys. I saw more people and then I see fewer. I'm not good at counting, but I have a feeling that, a sense like something is happening, something is fewer. Yes, I'm right. Why are you disappearing? Why do you hide your faces from me? So I need to see your eyes in hopes that I can see in your eyes whether you understand or not. Do you understand? Okay, not everyone is shaking their heads. Now, where do I lose you guys? Do you see this? It's not, well, it only seems tough. It's not, you see a lot of things, they seem tough, but they're not that tough. If I understand, it must be not very tough. Yeah, I know. When I look at myself in the mirror, I think, yes, scary. Here is what I'm saying. You expect that when you learn expected value. No. So here is what I'm saying, guys. For the first situation, for the event A, we have individual 1, 2, blah, blah, blah. Here are the last few individuals, right? So somewhere here it will be n minus k all the way to n. Good. So they are wearing their own. They're wearing their own hats, and so I have only in this case. In the previous situation, I did it in the beginning. But in my new modified version, I decided to make the last k individuals wear their hats. I think it should be n minus k plus 1 as first. I wonder if that's what, yes. Good. So this is why it's n minus k factorial over n factorial, because my sequence is determined on k points, on k nodes. K people are wearing their own hats, so my sequence is determined on k nodes, and it has n minus k degrees of freedom, if I may express it so. Good. That's why it's n minus k factorial over n factorial. Now here I don't need to do anything, guys. I just realized, ooh, and this is just person 1 not wearing his own hat 2, and n minus k not wearing their hats, and we already solved that problem. You understand? Given that the others are wearing their own hats, it's like we are having a smaller gentleman club where none of those are allowed to pick their own hats, which means that we're getting exactly that same summation. It's just that same summation goes from 0 to n minus k and not to n. Right, a smaller population. Given that k individuals of the club are wearing their own hats, now it's the same as if we play the game with a smaller club. Do you see that? The club containing n minus k individuals, and reduce it to a previously solved problem. The club with n minus k individuals, none of whom is allowed to wear his own hat. Yes, none of whom is allowed to wear his own hat, which is this formula. Now, if I push n to infinity, n minus k will also grow to infinity, and that summation will become e to the minus 1. But what about this n choose k times n minus k factorial n factorial? That is simplified to 1 over k factorial. You can see that clearly. So the answer is that the probability that k people wear their hats is 1 over k factorial times e to the power of minus 1. Interesting? So the most probable thing is, you see, 1 over k factorial will make it smaller. The most probable thing is none of them will wear their own hats. And then the more people wear their own hats, the less probable this becomes. Interesting, yes? Good. So this is, guys, something will hopefully you will practice, and that hopefully makes sense. It's not terrible. Now we begin considering Bayes' formula. How to condition. So recall that the event E is the same as E intersect the sample space, and the sample space can always be written as F union F complement. I'm basically going to try to condition event E on whether or not event F occurred or not. So all of you that love Bayesian statistics, please clap your hands. What do you do? Right? So what happens? So we have E intersect F union F complement. And that is E intersect F union E intersect F complement. Those events are clearly mutually disjoint because you cannot have F and F complement, yes? So that means that probability of E can be written as probability EF plus probability EF complement. Are you with me still, guys? I mean, I might have gotten lost if I had to listen to it. Yes, I mean, I tend to easily get annoyed. EF complement, whatnot. But the idea is very simple. Look what I'm trying to do. S is the sample space, Alice, right? It's the sample space. So what I'm saying is something like this. Imagine that, first of all, this is my full sample space. My full sample space, and I am interested in understanding the probability of E. And for whichever reason, calculating directly the probability of E is complicated, right? I do not know the frequency of E, so immediately within the sample space, but I might know the frequency of E relative to some sets F and F complement, okay? So imagine that, for instance, this set here is F, and this set here is F complement. Yes? Yes, so imagine that I look at this region, let's color it green, and for whichever reason I know what is the number in E relative to the number in F, okay? And I know this, the number, this is the number EF, right? The number of I should have said the number of EF relative to the number in F complement. Then the idea is that yes, you're right. Exactly, Sarah. I mean, S is the entire thing. You're correct, and so your agreement is valid. It's actually not important for S to equal to it. You see, I'm actually using some. You can see by my picture. You are obviously aware. Then I don't really need to know. I don't need F. I don't have to take events. It doesn't have to be F and F complement. It has to be two disjoint events that fully contain, or more, that fully contain E. But in the way I'm saying it, everything I'm saying is this is my S, right? This here is Thank you for the correction. This entire thing is S, at least in my setup. And there should be number of E F in relative to F, and number of EF complement relative to the number in F complement. If I know those quantities, I could figure out the relative frequency of E to S. Good. So in set notation, it's some people prefer it graphically. For me, easier to see what happens in terms of set notation. So E is the same as E intersected the full sample space, and the full sample space can be written as any F union F complement. And the intersection is simply what's in E and F or what's in E and F complement. And those are disjoint events. So the probability of E is the probability of EF plus the probability of EF complement. Good. And now here I can use conditioning. So what is this? This is the same as the probability of F times the probability of E given F, which if you prefer, you can write it in reverse. You can write it right to left, like in Hebrew. Good. It doesn't matter, multiplication is commutative. Clear? So this is where I use the multiplication rule. And here I use it again. And of course, what is probability of F complement? It's 1 minus the probability of F, which I can also reduce therefore to this final line. Now we're going to see how that's supposed to be useful, right? When is this situation happening? We'll see a few questions. So insurance company divides people into two classes: accident prone and not accident prone. Statistics show that an accident prone person will have an accident within a year with probability 0.4, whereas this probability is 0.2 for non-accident prone individuals. So we have to assume that they had some methodology in determining who is accident prone and who is not. Somehow maybe they checked, they made a psychological evaluation, right? Like for instance, I had to go to a psychologist and they told me, touch my right hand with your right hand, touch my left hand with your right hand, that type of thing. Because for me, when you tell me turn left or turn right, I always, if I don't know where I'm going, I usually decide when whatever you say it's already where I want to go. Right? I have to really rotate myself and place myself in your position so that I would understand what it is. Right? So maybe I'm accident prone, who knows? Clear? Yeah, you're not sure. Do you understand what I'm talking about, guys? I'm just saying they determine it. It's not important, but they had a way to determine it, let's say, right? And if you're accident prone somehow, then from that population of accident prone individuals, they have an accident 40% of the time within the first year of getting the insurance. Whereas if the individuals are determined to be from the non-accident prone category, do you understand? In other words, if you restrict your sample space to accident prone individuals, you will see that with frequency of 40%, in other words, 40% of the individuals on your list of accident prone list, they will have accident. Good. On the other hand, on the separate list of individuals that are not accident prone, only 20% will have an accident. Yes. So we have different sample spaces here, but we want to know what is the likelihood that a person we haven't tested will have an accident or will be accident prone. So let's say it's determined that 30% of the population is accident prone. Then what question is, what's the probability that a new policyholder will suffer an accident within a year of getting the policy? Do you understand? Because the new policyholder, we don't know if we place him on the accident prone list or on the other list. Let's see if you can calculate it, guys. All the best of luck to you. All right, Sarah, thank you. Wait a few more moments, guys, and we'll do it together. The lecture is over at what, 7:40? I forget. No? Hmm. All right. One more minute, guys, and we do it together. Thank you, Alan. Let's do it together, yes? So here is the situation. So A, the event policy holder has an accident, and I, the event policy holder, is inclined to have an accident, accident prone. So that's my labels, okay? A and I. Here we begin a new thing, guys, where you need to be coming up with good labels. You know, like how do you label the sets? It's another small thing that's different slightly maybe from Kafka Protocol. So then what's the situation? And those that replied, they replied correctly. So probability that you'll have an accident is either you will have an accident being accident prone, or you will have accident being non-accident prone. Do you agree? So you have two properties, right? That you are kind of having an accident and having this accident proneness stuck to you, or you have an accident and not having the accident proneness stuck to you, which then allows us to condition. You understand how I conditioned it. So it's A intersect I plus A intersect I complement, which I can then condition. Because what's the conditioning? This A given I means that now if you're accident prone, I calculate the relative frequency of A in I. So this is 0.4 This is in how much in population do you have accident prone people. So this is 0.4 times 0.3 plus this is 0.2 times 0.7 or 0.26. So far good? Yes, no problem. Yes, guys, that's important. We just begin it. And the ideas are very simple. You understand, guys, why we do that? Why is conditional probability here is applied? It's like we want the probability of an accident given both lists, given accident prone list and accident non-prone list. But we can easily calculate only the probability of an accident in each list separately, right? And they are not of the same size. I imagine that all the people are listed in either first or second list. I just do not have all the names available. It's encrypted. Make sense? So if a person has an accident, I try to calculate how much, what's the likelihood that what's the likelihood the person has an accident given on first list I know, given on second list I know, but altogether I do not know the probability. This allows me to compute it. So now next question, guys. New policy holder has an accident within a year of purchasing policy. What is the probability that the individual is accident prone? Can you calculate it? So we now know the person had an accident. What's the probability the person is accident prone? Is it very high or not very high? Okay. Okay. We have two answers. Maybe a few more come by. Thank you, Roada. Yoadra. Thanks, Jennifer. Thank you, Nora. Okay, thank you, Serena. Let's do it together. Here is the situation, guys. So I'm interested in probability that somebody is accident prone given that there was an accident, that the person was involved in an accident. Now, what do? So by conditional probability, this simply means the intersection of I and A divided by the probability of A. And here I can use my trick. It's not easy to calculate I given A, but it's easy to calculate A given I because we know that information. So do you see I have intersection of A and I can put them in any order I like. So what is this? This is the same as the probability of I and then probability of A given I. Do you agree? I can just read it from any direction I like. That's the multiplication rule. And the bottom is probability of A, which we already calculated to be 0.26. So in the numerator, we get 0.4 times 0.3, denominator 0.26. Altogether, we have 6 over 13 or 0.46. Everyone understands? You just have this easy trick, you see. If I have A intersect I can decide to condition on any one of them separately. And here is your very favorite question, guys. A multiple choice question with m possible answers appear on the exam. By the way, here is a very short question. You know, you have multiple choice questions. Do you know what you call them in Russian? Multiple choice questions. Any ideas? We call them American questions. Elaborate? What's there to elaborate? American questions. You know, you have option 1, option 2, option 3, right? The Russians don't think this way. So back to this. A multiple choice question appears on the exam and it has m answers. The probability that student answers correctly by guessing is 1 over m. In other words, you know, the answer is randomly one of the m possibilities. Usually m equals to 5 or 4, right? Or sometimes 6. Good, so 1 over m is the probability of answering it correctly by randomly picking. What's the probability that the student knew the correct answer given that he answered it correctly? That's a very interesting question. Yes, guys? If a person answered it correctly, what's the probability he knew the answer? And the thing is, let's say we have polled students and we know by statistics that the probability that the person knows the answer to a question is P. You understand? So let's say you just quiz, you interrogate a person, and with the ratio that amounts to P, the student knows the answer. So based on this information, calculate what's the probability student knew the answer if the question was answered correctly. P is the probability that you know the answer. You know, maybe it was investigated statistically without multiple choice. The person knows the answer. So just a sample that tells you about the population. So yes, you're saying the answer is P. Okay. If you say so. P over M? Okay, if you say so. Yes, Alan. When in doubt, 1 over E. I see people begin to abandon me, right? Your time with me, you're like my psychotherapist, I think, right? Once the time is up, you just quit. Yes, I call psychotherapists friends for hire. Yes, apparently they get paid by the hour. All right, guys. So since you haven't answered, and I'm sure it's keeping you in suspense. Oh, I see. Erin looks right. Let me see. Do you want to hear the answer, or do you want to be kept in suspense until Monday? You don't want to be kept in suspense?
No.
Suspense. Here you see. Some people say suspense. Okay, great. I'll keep you in suspense until Monday. I'm sure it will be torturing you all weekend. Yes. Any update on midterm? Yes, I'm considering to make it hard. No, you're not, Jack. You're right. You're my victims. Goodbye. Or if you want to stay, guys, we will talk about exams.